have seen application method set. Can you please
Sir, you're not audible.
now? Can you hear me now? Hello.
Yes, sir.
Yes. Okay. So look at these micrographs as well as the macrographs. What happened? Hello. Okay.
You're
So
audible,
look
sir.
at, yeah, okay. So look at these micrographs as well as the photographs and quickly tell me what are the fabrication methods we can have. I mean, with the help of that, we can fabricate this. So you look at these thin films, either we can go with the melt mixing method or the solution casting. Through that, you can obtain these films, and this is nothing but the multi-layer films. So again, this also can be done through solution casting or the melt mixing method. And this is, I mean, another method kind of uh, fabricating the porous structures, maybe with the help of salt leaching method or using a lyophilizer, like kind of freeze drying approach. Yeah, that also we'll discuss now. So if I ask you to fabricate this kind of 3D structures, okay, so how do you fabricate? What kind of method do you adapt? You cannot adapt none of the method what we have seen so far, either solution casting or kind of I mean deposition like laser deposition or electro deposition something or melt mixing or any kind of method. So none of the I mean method can give you this kind of I mean 3D I mean structures. Okay. So there comes the techniques called 3D printing or the additive manufacturing methods. Okay, where you can fabricate any kind of complex geometry of your planned structures. Okay, so it's nothing but kind of I mean construction of a three-dimensional product or the object with the help of CAD model or the digital 3D model. Okay, and 3D printing can also be referred to as a variety of process in which the material is deposited or the joined or the solidified under the I mean computational approach to create those 3D objects. And the materials are being added together. That means it's like kind of layer by layer approaches. Okay. So one of the things you can see here, you have got a plenty of layers. Of course, we do have, I mean, two different materials. Okay. So that means the during the process or the meantime, you can have a multiple layers which are, I mean, having distinct materials as well. One can be of polymer and another one can be of some composites, etc. Okay. So, so we do have different types of 3D printing or the additive manufacturing. So one of the method is called extrusion-based additive manufacturing. That means uh, kind of same like the extrusion melt mixing. So you're gonna melt your polymers or the substrate, and subsequently you're gonna apply certain pressures, etc. And then that is going to be, I mean, printed or I mean, pushed towards the orifice, and subsequently you're gonna have the structures. I mean, with the help of those CAD design. Okay, so you can see here we have plenty of types like I mean fused filament fabrication based extrusion additive manufacturing and direct writing based one. Okay, that means like filament means the substrate or the material which you want to print or the I mean use for additive manufacturing. That will be directly that is going to be melted, and subsequently those melted I mean the molten metal or the polymer will be deposited on the substrate. Okay, and you have a kind of cartridge. Okay, and cartridge is nothing but once the filament is melted with the help of heater. Okay, so where it carries those molten material or the polymers, so that we usually call them as a cartridge. Okay, and this head, I mean, the cartridge can be movable X, Y, Z directions. Okay, So as a result, it can move into the, I mean, two direction as well as once the first layer is done, again you can lift it up. I mean, the Z direction, again you can deposit the second layer. So likewise, you can dispense the material actually, or we also use them the terms called ink actually, because the moment when you say 3D printing, the materials, I mean, what we use for the printing material, which is usually we used to call them as a ink actually. So the ink gets dispensed from the cartridge and subsequently I mean, deposited on the substrate according to the design you would like to have. Okay. So that is called, I mean, filament based one. And direct write means you are going to dissolve your material. Okay. So if you are using protein or the polymer, you're going to dissolve them in the suitable solvent, even in the aqueous media. So eventually it transform into the paste or kind of viscous, I mean, liquid. Okay. So, so of course, the viscous liquid has a different characteristics. Okay, they also do. I mean, get cross-linked at certain environment. Okay, so you prepare the ink. I mean, hydrogel or the viscous paste, and then you take them in the cartridge, and then you can apply the same pressure. I mean, extrusion method like. There'll be some sort of, I mean, pneumatic pressure or the air pressure, something. With the help of that, you can, I mean, move this cartridge head and then you can print this, I mean, substitute whatever you have. So again, you have a different, I mean, things like this patterning of this, I mean, strands or the, I mean, the printed format like each layer. So you have a different whites also will start to form. Okay, to get rid of those things, you have a different patterns to avoid those formation of whites actually. Okay, of course. See, look, I mean, whites are also good for certain applications, and these whites are not good for certain things. Like, say, for example, this printing aspect. I mean, 3D construct can be also used to fabricate scaffold. Okay, so the moment when you talk about the scaffold, I mean, we also deal with the cells. So cells need porous structures so that they can interact more, and as a result, the proliferation or the differentiation will be better. So yeah, the design aspect, like according to the application and the properties which you are targeting. Okay. In extrusion-based additive manufacturing system, it has also been developed for, I mean, developing some of the biological materials and which are called bioprinters. Say, for example, these materials, I mean, the viscous hydrogel or the paste actually, can be used to fabricate tissue and organs in the lab. That means you're going to prepare the viscous paste with the help of proteins, okay? And then you're going to add the cells, and subsequently, the cells along with the hydrogel is going to be printed, okay? According to the design and you want to have it, okay? That is called bioprinter, okay? And of course, the bioprinters can also deposit various biopolymers, hydrogel, and encapsulated multiple cell types in the hydrogel to produce 3D bioconstruct. So I'll show you a couple of images. So these all these stuffs, I mean, tissues or you can say organs, okay, which are developed in the lab. That means you can see your blood vessels, okay, so which are, I mean, printed by using additive manufacturing techniques. So it has got two different types of cells actually, okay. And of course, you can see the laboratory developed 3D printed ears, okay, which has multiple cell lines, stem cells, and then I mean, HUX cells, I mean, endothelial cells, along with the I mean, the ear-based specific cell lines. So, 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 what is the fun of having this thing in the lab? Any idea? So why to develop organ tissues in the lab? You know, the transplantation issues, right? So wherever you go, I mean, kidney transplantation or any other, I mean, implant, etc. So we are short of donors. So who is going to donor? For the transplantation. So even if you see the, I mean, the NIH website, I mean, the number of donors and the number of waiting lists, okay, which are pretty less actually. I mean, waiting list is of course pretty long. So the who can donate, I mean, the nominated list actually, which is very less, and who is, I mean, who is in need of implant or kind of organ tissues, which is pretty long actually. So in fact, like um, I have done one this one survey. Yeah, you can see here the recent survey here, like February, which was I have accessed on February 2021. So as of now, 107,000 people are in the waiting list for the organ or the tissue transplantation. Okay, and only 39,000 was done in 2020. Okay, and you can see, I mean, how much the ratio, I mean, in the waiting list as well as, I mean, which was successfully done actually, which is we cannot match at all. So there comes the question like, instead of waiting for the donors, why don't we fabricate those tissues or organs in the lab? Okay. So once you start to fabricate them in the lab, it is very easy, right? I mean, whoever need even a kidney, you just fabricate it and then implant it. Fine, the job is done. So of course, I mean, this is very, I mean, it's too early or the beginning stages of this work. So, but still, I mean, people are doing, and I hope, I mean, another, I mean, 5 to 10 years, things will be resolved actually, these organ donation issues. So you can do anything. Say, for example, the if you have the I mean kind of core shell based one, like to fabricate those coaxial based strands, you can also do that. Okay. So in that case, you're gonna use two different bindings, which is having a distinct hydrogel or the cells. I mean, which carries the binding. Okay, and you can print them as well. Say, for example, if you see the blood vessels. On top of the layer, you can see the fibroblast along with the several proteins, and the inner layer, if you see, they are like endothelium and combined with different proteins. So why to fabricate this kind of thing? Because you have to mimic the same as same that of the native tissue architecture. Exactly like what kind of cells they have and what kind of morphology, whether core shell based one or kind of some multi-layer structures, etc. So, so the 3D printing is the one of the technique. It fulfill, I mean, all kind of those requirement. Like if you want to fabricate coaxial, or if you want to fabricate like kind of core shell, which has, I mean, different porous structures. All those things we can do it here. And have you ever come across this one, lab on a chip, microfluidics? What is lab on a chip or the microfluidics technology? Is very new or what for you? You never heard about this? So microfluidic is nothing but it's a
No,
yeah. Was that Utsav?
so no idea.
No idea.
The
Fine.
deputy.
Yeah. See, you have I mean microfluidics. I mean we do have a certain journal itself. You can if you are interested, you can go to there as well. So RSC lab on a chip. You have one dedicated I mean journal where they mainly talk about the microfluidics and I mean lab on a chip actually. Okay. So, I mean, it is one of the excellent journal, and you find, I mean, plenty of applications, not only biomedical, I mean, materials aspect, like other applications. So, microfluidic is nothing but like you are going to fabricate or mimic the, I mean, bulk system into the miniature type. Okay. So that is what they call lab on a chip. I mean, the chip can, I mean, you can design the whole lab on a chip actually. Say, for example, the best example the how the polymer industry works. Say, for example, polyethylene. Okay, so you take monomer gas, ethylene gas, and then that undergoes, I mean, pressure. I mean, they take it to the, I mean, low pressure to convert them into liquid, and then they add the catalyst, etc. So if you see the planet, I mean, it is pretty big. So all those things you can mimic in a single chip actually. Okay, with the help of any fabrication technique. Okay. So once you do that, what we can do, you can optimize all those. I mean those trial method, everything in the very, kind of very small volume materials. You don't have to go for, I mean, carrying those kind of kg raw material to make sure that it is working or not. So of course we do in the laboratory also you can optimize. I mean for the new I mean ideas etc. But still to reduce that, people have come up with this kind of microfluidic things. Okay, to mimic to have those miniature type of things on a chip actually. This is one aspect, and other one like this is one example. We have plenty of miniature or the lab on a chip based applications. You can say microfluidics or the lab on chip. The another one which is I mean widely people use in the biomedical sector is that So, you know, like how the drug is getting commercialized. First, they investigate it in the lab, and then, yeah, of course, they do all those screening in the in vitro analysis, like cell culture, the drug delivery, etc. And once that is, optimized, and then you going to do with the animal trial. Okay. So animal also you will have to get permission from the animal ethics committee, and then you're gonna try different animals, like very small animal to heavy animals like wild animals, because you should make sure that this is not harming. None of them. Okay. Then once that is screening is done with the animals, and then they'll go with the human trial. So you see how much the energy and the spend, and how much the animals are going to kill, etc. So all these things you have seen. So what people have done with the help of this microfluidics, they have come up with that miniature of those all those experiments in a chip actually. Say for example, why they are going to test it in the animal? Say for example, they are developing some drugs to get cured in the for bone injury or kind of some wound dressings, etc. Okay. So what they are going to do, they are going to develop those miniatures in the lab. I mean, on a chip actually. So what will happen the moment when you are getting injury on your skin? So there will be a scratch on the skin. And then there will be blood comes out. So all those kind of things they try to mimic in the mimic on the chip actually. Okay, that means they are developing the skin in the on the chip, and once they developed, they are going to induce the injury actually with the help of any kind of either chemicals or kind of we have different setups where you can disturb specifically those cells. Say for example, you have developed the skins on a chip, and if you want to disturb only the the fibroblast cells, we'd have certain chemicals where you can specifically disturb those cells. Okay. And once you disturb those cells, that means your fibroblast cells will start to die. And then once fibroblasts start to die, means your blood cells, HUVEC, will also start to, deteriorate, or the healthy cells will be reduced. And then you add the drug, okay, and then you see how the cells are getting regenerated, okay. So this is one of the aspects. So likewise, cancer therapy, all those things people are done actually with the help of this microfluidics. So now here comes to the questions like why 3D printing is also used for lab on chips or the microfluidics. So again, the same thing, like if you want to fabricate a layer by layer approach, like one layer can be of fibroblast and the another layer will be of POG based one, and the next layer another one protein based one. So all those three-dimensional picture, the structures cannot be done with the help of other techniques. Okay. So here you can see one of the examples, like at one chip actually they have fabricated kind of different structures they are mimicking, like a bone also they mimic, and then heart, and then livers, etc. Okay. So to target certain disease, or to finding out those drug screening, etc. So this also can be used, for fabricating those kind of multi-layer structures for, drug screening, and what else can be used? Yeah, that's it about this 3D printing approach. Yeah, properties, of course, since you are printing and mimicking the same tissue architecture, as a result, of course, the performance or the properties will be pretty much good as compared with that of others, other fabrication method, because other fabrication method usually produce 2D structures, not the 3D one. And yeah, now, so you have seen all those structures, how to fabricate. Now we will see one of the paper, like drug releasing or the encapsulation efficiency, how good it is. Okay, of course, which one will have a more drug loading efficiency here, according to these four structures? Yesterday also we have discussed this one, but yeah. So you have a film, and you have a multi-layer film, and you have a porous scaffold, and then you have a 3D printed structures. Which one will have more drug loading efficiency or encapsulation efficiency?
3D printed structure.
Yeah, followed by that.
The porous structure.
Okay, fine. So now question comes how the releasing effect will be there. Say for example, we have loaded of like kind of 100 mg of drugs into here and here there. Of course, the loading efficiency will also be varied. Here 100 mg means I'm sure will not be having 100 mg, maybe of here 80 and 70 or maybe of 30 or 40. Okay, so I mean, right, our tablet, like if you take tablet and they will not, release, all the drugs, instantaneously. Because if any drugs, if they release instantaneously, the moment when you take, they'll induce all those side effects actually. Okay, because the drugs should release at the desired targeted tissue or the organ, because which was, damaged or the the disease which was happened at those desired places. So as a result, we have terms like sustained drug release and then robust drug release, etc. Okay. So sustained drug release means the drug is releasing at the desired targeted tissues and the organ over the period of time. So it start to release very slowly. Maybe of 3 days or 4 days and 5 days. Okay. And we do have another one terms called burst release or the robust drug release. That means the drug release very instantaneously. Okay, like kind of if you have loaded 100 mg of drugs in the carrier, okay, and almost like 80% of the drugs will start to release. Immediately. Okay, so most of the disease, which is this burst drug release is not favorable because as I told you that it induces a lot of side effects. Okay, so how to control them and how to get rid of those bust drug lists, etc. How to achieve those things, because by playing with the role of different structures. Okay, say for example, if you have the structures like this, very porous structures and multi-layered film or this kind of 3D printed one, so you have a lot of option where you can release the drugs actually. But in case of here, the single layered thin film, there's no option. So why? Because the drugs usually start to absorb on the surface of the film, and the moment when you expose them in the targeted tissue, of course, all the drugs will start to release. Okay, because there is a mismatches. In the temperatures as well as the pressures, etc. As a result, if it is physically loaded drug, they will start to release very fast. And if it is chemically released one, of course, you can control it with the help of laser light or any kind of radiation sources. Okay? So again, the structures play a key role for having those controlled drug release or obtaining those reducing those burst drug release. Okay? And top of that, actually, so you can also play around with the materials actually. We have seen composite and then we have seen different materials like, protein based one as well as metal and other ceramic based one. Okay. So now I'll, give you one of the examples, show you one of the example how the nanomaterials, that means the morphology of the nanomaterials, how it's playing in the role of drug delivery. We have discussed one-dimensional material, two-dimensional material, and three-dimensional material. So now we'll see how one-dimensional is helping for drug releasing characteristics, and two-dimensional material how they are helping in the drug releasing characteristics. Okay. Yeah, yeah. So we have seen one of the materials called one-dimensional, sorry, 2D material, nanoclay. So we have a different morphology also. We have seen intercalation, exfoliation, and then flocculations. Okay. And this example, we have seen how the intercalated morphology is helping to improve the barrier properties of the composite. Okay, through the Sartorius diffusion path. If you have these intercalated structures, as a result, the diffusion path will be pretty long. And of course, if the gas want to diffuse faster, they have to find out the path through the polymer matrix actually. Okay, and they cannot diffuse into the ceramic particles because clay is made up of ceramics. So now we'll have one of the examples, of 2D materials for drug delivery sectors. So you see here, you have a two different morphology. Okay, clay, of course, the I mean, the material is clay nanocomposite. So the left side is, I mean, which is intercalated one, and right side is exfoliated one. Okay, the pink one is drug actually. So you have a nanocomposite structures, and the drugs are embedded into that nanocomposite. So you assume that they are physically loaded. Okay, so since they are intercalated one, what will happen? Say suppose if this drugs want or this drug wants to comes out, what will happen? So they have to find out the randomness or the free volume presence in your carrier. Okay. So of course they cannot diffuse through that clay particles because I mean the refractive index is pretty high, and as a result they cannot diffuse that easily, and they have to pass through the polymer matrix. I mean through that chains. Okay. So look at here. If you have more of intercalated structures, mean they will have to, I mean, travel all the way. I mean, to that. I mean, adjacent to that of nanoclay. Okay. As a result, the mean travel path will be pretty long. Okay. So as a result, what will happen? The drug will take long time to deliver actually. Okay. Of course, the drugs, I mean, whatever the drugs which are absorbed on the surface, they will start to release faster. And whatever the drugs which are absorbed on the, I mean, inside the composite structure, they will take more time. So as a result, you will end up with the sustained drug release or the controlled drug release characteristics. So sustained and the control is control both are same. And look at this exfoliated one. Okay. In case of exfoliator, I mean, you can see here there are more free volume is present in your material. I mean, the composite one, and the mean travel path is pretty less in exfoliated one. Okay. So as a result, even the drugs which are inside that nanocomposite structure can also comes out very easily. I mean, that means the drug will start to release immediately. Right? I mean, robust drug release are the, I mean, ultra fast drug release. Okay. So, so as a result, what will happen once the drug is released completely, then you will end up with a lot of side effect, and that is not, I mean, usually favorable. Okay. So, so with the help of this morphology with the same nanomaterial, but if you can obtain the intercalated one, then you can have those kind of sustained and the controlled drug release. And if you end up with the exfoliated morphology, then again you will end up with this kind of I mean burst drug release. Okay. So likewise, I mean, if you use one-dimensional material again, that will shoot up again the burst drug release as compared to the of exfoliated one. So if in case of drug delivery, always you can go with this kind of 2D morphology based nanomaterial reinforcement. And yeah, I mean, depending upon the property, you will have to choose. In case of if you want to improve the mechanical properties like a toughness and all, of course, intercalated will not be that helpful. But if you can have this kind of exfoliated structures, you can enhance your mechanical properties significantly compared to that of intercalated one. Yeah, so I stop here. Maybe we'll see in the next class about that drug loading efficiency in one paper actually. So with the help of UV spectroscopy, how they are calculating the drug loading efficiency as well as their mix characteristics. So, so others can leave, and maybe Ashutosh, you wants to discuss about assignment, right?
Yes, sir.
Yeah, you stay back. Thanks, others. Fine.
Thank you, sir.
Yeah, what is your doubt, Ashutosh?
So in
So
that
actually,
one, yeah, sorry,
yeah,
you go.
actually we try to find some materials, but we are getting only same fillers, but not the same matrix for that filler because in melt mix process, like if we are going for graphene oxide, then there is PVA, and
Yeah.
then for that same process in C2 there is PMMA matrix with graphene oxide. So the matrix will also change the properties, right? So there can't be there isn't any polymer with the same filler and same matrix so that we can compare it like that. That's the thing we wanted to confirm, that if we can go for such examples.
Which one of a PMMA and graphene? Huh?
Yes, sir. PMMA and graphene, PMMA matrix and graphene
Okay.
filler.
Okay. Just see here in situ polymerization also they obtain, and sometimes you'll have to change the matrix. If you don't get, you'll have to change the matrix.
Sir, we
Yes, so
tried doing that, but
Still you're not getting, huh?
yes, sir, we are not getting the exact same composition for the matrix and the pillar thing.
Sir, and even if we get a paper having the same matrix and fillers, either the properties part won't be there. Like they'll be comparing based on the different types of solvents used or something.
Yes, sir.
Some changes are there as a result. The properties are completely different, huh?
Yes, sir. The properties is not like comparable to each other.
Okay.
So we
Yeah,
want to.
I understand it's a tough job, but so you find you whatever you tried actually. So it's not looking for none of the, I mean, matrix composite structure or what? Hello?
Sorry, sir, I didn't get that.
No, it's you're not getting for none of the combinations or what? For none of
Yes, sir.
composite.
It's so for example, I told last class also PVACNT, and and one more I have tried with this SWCNT, the single wall and the multi wall. But the point is that when we go from single wall to multi wall, the properties changes a lot. So there is no comparison between the solution and melt and then in situ, because I find this in situ in multi-wall, but no in single wall. But solution and this thing melt mixing was there with the single wall, so the properties were not comparable to each other. So, sir, we wanted to request either please make this assignment a bit easy, or please change this one.
So fine.
Or how should we go about
See,
actually?
See, I mean, I want you to refer some of the articles and make sure that what are those fabrication technique you have studied and what are those advantage and their disadvantage. And
So
yeah,
that we can easily compare the basic properties and the basic advantages that the in situ gives in
fine.
comparison to others. But with respect to the same composition of nano composite, it's not that
You're not getting
easy,
it.
or maybe I'm not getting it actually.
Yeah, probably. I mean, you'll have to try a lot of stuff like different copolymers, etc. Fine. See, Ashutosh and others, you whatever you have referred, you just write it and please upload it, and you do not have to worry about the marks. And yeah, that's what I can say. If you learn something, and maybe we'll have some at the end of this course, we'll have some viva wise. So according to that, I'll decide the marks for your assignments. Okay, you don't have to worry
Okay,
about marks. So once you are
okay,
thorough with the concept, fine, go ahead. Okay.
yes, sir. Yes, sir.
Anything else? So say for example, actually, if you refer that my paper, what I have given you for, no, I didn't give you assignment, I guess. Wait. There are some paper, they does everything, in situ polymerization and solution casting, mixing, everything. Of course, I mean, it's tough to get, but still you have to find. I mean, you should have some patience here and there.
So that that you're discussing everything in a one paper. I got that one paper. It is on some um, polymer, graphene, or some CNT, or maybe something like that. But they just gave the preparation process. Like they just gave us how it will be processed through melt mixing, casting, and the solution casting and the in situ. But they did not compare any of the properties. So again, it was worthless to go through that.
Say, for example, not this paper, sorry. this paper, no? So they compared everything, in situ, and then melt mixing, everything. So, and they have studied the mechanical properties as well. So all these things you can read here, and their reason also they have given, like what exactly playing here. So fine, I understand you're spending time for your placement also, I guess, huh? Don't have much time.
Yeah, yes.
Fine, you upload it, and whatever stuffs you've done it right, that you write it properly and upload it, and rest other things maybe, yeah. Regarding this assignment, we will have some viva wise, and according to that, I'll decide the marks.
Okay, sir.
Okay. Anything else?
So we
Yeah.
have to search only for like polymer-based nanocomposites or the metal.
Anything, metals also you
met-
can, yeah, metals
it's
also
fine.
you can go ahead, yeah.
Okay.
But sir, on that Iris page, Moodle page, you wrote that only polymer nanocomposites are to
Is
be
it?
considered.
Okay. Yeah, but maybe I unknowingly written, but you can select any other metal also, ceramics also, and see their,
Okay,
I mean, properties.
okay, sir.
Okay, that's it, right?
Yes, sir.
Okay, fine. And
Yes.
you go to that link, and yeah, I think you'll get all those things.
Okay, thank you, sir.
Yeah.
Thank you,
Okay.
sir.
Yeah, fine. See you.
Yeah, thank you.